Just doing a quick audio check. Okay, that seems to be working all right. Let me just make sure the keyboard's not crazy. Keyboard, crazy? Hello and welcome. I am glad that you are here, and today we are going to have a little bit of fun with prime numbers. And for that, I guess I'll start with a little bit of background. So, for those of you that don't know, my name is Brendan, and this is Dev Chatter, where we are going to have a little bit of fun writing code on a regular basis and probably talk to some other developers about things that they are passionate about and generally improving our code as we go. I obviously want to learn from you guys. I assume you guys want to learn some things from me, and we'll just figure out what we can from each other and see how that goes. So today I want to talk to you about I guess the program that we're going to write. It's fairly simple. We're going to do it in .NET Core because .NET Core is fun and I like it. We will be writing some code that I used to have interns write in their interview in a few consulting firms that I've worked at in the past. Now, the reason that we liked these programming exercises is because they were fairly simple. So we expected someone that was in college would be able to work on this without much difficulty, and it wasn't going to be some massive challenge for them. The other nice aspect of it is that it doesn't take that long to write, even if you try to do it well. So you could take the time to write unit tests. Most of the intern candidates did not write unit tests, as that was not part of their college curriculum. However, you do run into some that will. Even those that did learn about unit testing in their program don't always do it in the interview. Now, I assume this is because it hasn't really been like beaten into their brains that yes, this is how you do it every single time. So we're obviously going to start off with unit tests being the main focus of how we do it. I might do a couple of pieces from what we would have them do, and I'll sort of explain along the way. So I mentioned that we're going to have prime number fun. So the bit of prime number fun that we're going to do is we are going to write a program that prints out all prime numbers less than 100. And this is the exercise that we would have them do. Now, the code that we wrote at that consulting firm, well, any of the consulting firms, I've never worked at one where mathematics was really the problem we were trying to solve. However, the goal isn't whether or not they can solve a mathematical problem. The goal is to see how they think about these problems. So whether they can reason it out and solve it. So it's actually better if they don't know all that much about prime numbers and more think of it as this is an unfamiliar problem territory, which comes up all the time in consulting. You are not the expert in the domain, someone else is. So in this case, I as the interviewer act as the expert in prime numbers. And I can talk with the candidate, so the interviewee, as they try and reason out a good solution. So it works out nicely. Additionally, we always did everything in C#. I like having someone interview in a language that's pretty easy. If they're much more comfortable in some other language, something different. So if they come from a C# background, Java background, C++ background, anything where C# is going to be pretty easy for them, yeah, we stick with C#. If they're not used to that kind of programming at all, I might let them program it in a language they're more familiar with. However, it then gets harder for the interviewer to know whether or not their solution is an effective one. Because there might be something in their language that does some trick that I don't know about. So the place that we're going to start is with creating a unit test project. You'll notice that I have a couple of things in Visual Studio already. The couple of things I have are a console application and a class library. So the class library is what we're going to test primarily. It is going to be our actual prime finding piece, and the prime finder console application is actually just what's going to print that information. So someone's going to run the prime finder, it's going to use the prime library behind the scenes, and during development we're going to use our unit testing framework to build this for us. Give me 1 second. Okay, I figured I'd put in a little bit of background music, just so we have something going. That should be nice and soft, you should barely hear it. Okay. So, where we are going from here. So the first thing that I want to point out, we're in .NET Core, and that is going to have a couple of significant things that go along with it. In .NET Core, it became much more common to use XUnit as your testing framework rather than NUnit, which was the primary testing framework in the classic .NET days. I think a lot of this came about because the internal Microsoft team was using XUnit for their work. So I'm going to go ahead and just make a unit test project. I'm just going to call it unit test for now because we're just doing a little programming exercise. This isn't, long term, although that bites you anyway, but a rename's a pretty easy thing, so I'm not terribly worried about it. So we now have a Hello World program and some unit tests. So I'm going to go ahead and run things, just make sure I didn't mess anything up. And it opened this on the other screen, but there's our Hello World. Let's see if it opens in the correct place now. Nope, it's always going to open on the other screen. In that case, what I can do is bring up PowerShell, bring that over to this screen, and I am going to navigate to that folder. So, hang on, I'm going to jump there. It'll be a little faster that way. Okay. Okay, so we are going to run the prime finder, and then whoops. Okay. So there is our Hello World program. Works like a charm. So from here, we can do a couple of things. So the first one that we're going to do is fix some of these little names we've got around, because we have unit test 1, we've got class 1, whatever. I don't mind our Hello World right now. but I just want to get a couple of things the way I expect them to be. So I'm going to call this the prime list generator, maybe. As I think, to start off with, I think the easiest thing to test is going to be if I have my class return back a collection, and then I can just check through that. I think that'll be the simple way to do it. Obviously, I would expect a lot of people that were starting out writing this to start right here and do a for loop. And one of the best approaches that I like is to start off with this as the starting point, where they just print out the numbers. So I'm going to say I and then plus comma, because I'll still do the same thing that someone else would do. Okay, so our starting point, we don't want to start at 0. I mean, obviously I could print that one, but prime numbers, and we would always give people this as the definition. I like giving this definition. A prime number is defined as any number that contains exactly 2 divisors, 1 and itself. Now, the reason I like saying exactly 2 and 1 in itself is that this defines that 1 is not a prime number, because it only has 1 divisor, and that is, 1 and itself are the same. Whereas with 2, it has 1 and it has 2. So I like that definition much better, because it clarifies that. Because a lot of people will say, it's only divisors are this and this. It's like, but I like saying exactly 2, because it's very clear. So now, if I go ahead and I run this code, now instead of hello world, I should get a list, and I've got a trailing comma, not going to worry about that right now. Okay, so clearly all the prime numbers. Or, obviously not. Okay, so if this is my initial set, I'm going to go ahead and steal this. That's usually where... I love it if people start the program this way, because whenever a candidate shows up and starts like this, I get the idea, they're making sure everything's working. Because I could have messed up anything in those libraries. So this just resolves the problems. So I am going to go ahead and wire up a couple of dependencies here, because I didn't do it yet. So I'm going to go ahead and add a reference to the prime library from the console application. And then in unit tests, I am going to add a reference just to the prime library also. So I'm not going to have that reference the console application. We're not going to test that right now. Now, yes, I know I could test that, but we're keeping things simple on the stream for now. We're going to work on some real projects later, but while I work out the kinks for the stream, as this is the second dev chatter stream, so I just want to make sure that we get things working nicely before I work on anything too real. So the next thing I want to do, so I created this prime list generator. So I want to go ahead and start structuring my tests in some way. So obviously I made a folder of just unit. I made a project of just unit tests, and inside of that project I want to create a folder. So I'm going to make the prime list generator folder, because I want to try and, at least for now, and if this were continuing on, we'd refactor it later, but for now I think it makes sense to have a prime list generator tests folder. Inside of this, I'm going to put my initial unit test class, because why not? And then I am going to fix this namespace and change the test. So the approach I like here is I like to have names that are clear about what it is we're doing. So when someone reads this, they're going to say something like, okay, so for the prime list generator tests, the such and such and such and such should do something when something happens. So it sets up this nice structure. So what I usually like to do, and there's a lot of preference to this, I usually like to say something like, okay, so I called it the prime list generator. Prime list generator dot get primes under up to, I don't know, figure it out in a second. So, and then going to underscore should, and I am actually going to tell configure, I'm not sure. All right. I don't have my settings configured for ReSharper to ignore these things, so I'm actually just going to follow its naming for now, but I usually like to have an underscore in there, and I don't want to go fiddling around with my settings while on stream, so I'm just going to leave it like this. So get primes under should, and then I'm going to say return empty collection, and this one I am going to do it, even if it's going to underline it. Return an empty collection, given limit of 2 or lower. Okay, so in order to make this work, I need to get my prime list generator. For now, I'm not expecting that this is going to have any dependencies, so I think I'm going to make it static. Now later on, if I do need to give it a dependency, I might change that, but it seems like it doesn't have any dependencies and it's just going to work the way that it does. Most of you probably know I'm not a big fan of having too many statics, but this thing really doesn't seem like, I mean, it seems like it's more a math thing than anything else, and a math thing seems like it should be static. I mean, if I think of all the math library pieces, like say math.square root, I'm effectively doing that. It'd be like if I had like math dot, divisors or something like that, then that should actually be an interesting piece to make. But anyway, so the prime list generator, and then I am going to call it get primes under, and we're saying, okay, I was going to type 100, but we're not doing that one just yet. We're going to do 2. So 2 or lower, we said, and this is going to we're going to say var prime list equals that, and we are expecting actually we're going to say assert empty prime list. So we want to assert the prime list is empty. And I am going to create this method. It is going to return an IEnumerable of type int. So we're going to have it return back the integers. And this is exclusive limit. I'm just going to make sure that I call it exclusive so that anybody that looks at this remembers, hey, that's, not an inclusive number. We're not going to include it. So if I put in 2, like I did, we expect to get back an empty collection. So first things first, let's go ahead and run these tests. Just make sure that it all works as expected. We're expecting a failure, because obviously it's going to throw a not implemented exception. Okay, so there is our one test failure, working as we thought it would. And if we take a look, it's a throw not implemented. Okay, I can fix that. We're going to go ahead and implement this. So return new list of int, and done. So now, when I run this, I should go ahead and compile again, and we should get empty collection success. Okay, cool. So the next thing I want to do is write a test that's going to fail. So I could expand on this. So right now I said limit of 2 or lower. So obviously I should put in something other than 2 when testing that also, but I'm not really ready to check that one yet. So what I want to do is say return, and I'm just going to say only 2 given limit of 3. So I want to confirm that when I pass in the number 3, the collection contains only one item. I am expecting 1, and I want to do the count of this. So one other thing that bugs me, Oh, okay. One thing that bugs me here is that by default I returned an IEnumerable. So I love IEnumerables in a lot of places. I happen to know that at least right now I'm going to be returning the list. Now there's some debate over whether I should return that or that. What I like to do is if I think I'm always going to probably be returning a list here, which at least for now I might be, I can get away with this. So if I need to change to an IEnumerable, I think I'll be able to. But I'm going to move forward with it like this. So what I like to do is give you an amount, like, if I don't think I'm ever going to change my type, I'm going to offer you back the most useful item I can. So in this case, I might be better off with an iList. But then when accepting parameters, I usually like to be as permissive as I can be. So I will take in an IEnumerable as a parameter and return back something like an iList or a list. Now, if I do need to change the code at some point, yeah, that can bite me a little bit, but I tend not to try to future-proof things too much, because we could do that all day long. So, there's step one. Okay, so at this point, we're saying we expect to have a single item, and you know what? I'm going to go ahead and confirm both that single item... Actually, what's the overload of single have? Can I say what it is? I think I might be able to. I'm gonna go ahead and try it. So we can have a predicate, an int predicate. So I'm gonna go ahead and say x equals 2. So we're expecting a single one where x is 2. So we're expecting the list to be completely just one item, and that that there is exactly 1 2 in the collection. Yeah, I think that works. I like that. So let's see what it gets us. It should fail, because yeah, it contains 0 elements. So now what we can do is say this. So I'm going to go ahead and extract this out as my list, and we're going to find this as, oh yeah, primes under, that's not bad. Okay. And we're going to say if exclusive limit equals 3, primes under, add 2. Okay. So now, when I run this, we should get a passing test now. And we do. So, obviously that's not really the code we want. And I just noticed that I need to rename that file. So I'm going to do that now while I'm thinking about it. And so the next thing that we would want to check is I want to confirm that the same trick works. Return 2 and 3 given limit of 4. So I'm going to give myself a limit of 4. I'm no longer expecting a single. I'm expecting there to be a 2. I'm expecting there to be a 3. Assert equal to prime list. We'll see if it suggests something on that also. No, it doesn't. Okay. So now I'm going to run this one. We'll see what it gets us back. So assert equal failure. Expected 2, actual 0. So I didn't get back any items. Wow. Wonder why. My code looked so right. Oh man, I'm an idiot. Oh, okay. Greater than or equal to 3. There we go. So then I'll make that was a joke, by the way. So now we should get to the next assert in there. kind of surprised it's not telling us what those are. But, so expected 2, actual 1. Oh, okay, so it didn't actually put the number in there. So what we're going to do now is one slight change. So I'm going to go ahead and put our little for loop in there, because we actually need to do this now. So I'm going to go ahead and say for, and we're going to go ahead and, instead of going up to 100, we're going to go up to exclusive limit. And then we are going to add I instead of 2. Yeah, I know I could have just jumped to an if statement and added the next one in there and been like, if greater than 2, add this one. If greater than 3, add this one. But that, you know, I've had enough joking around with you guys. I'm just going to put in the real one there. So, there we go. This clearly finds prime numbers. See? Works perfectly. Okay. So, now that we've got that, I want to make some changes here because this is going to get out of hand quickly. So, I am going to work under the assumption that a higher number is not going to break things. So, I am going to start putting in some test data here. So, for those of you that are used to NUnit, you're used to this class having a test fixture on it, and each test method being called a test. If you're used to NUnit, it's going to be a test class and a test method respectively also. But in XUnit, we are instead going to have fact, and we're not going to mark the class at all. In addition to fact, we can have a theory. The theory, we can do something called inline data. So essentially what we're going to do here is just hard code in a little bit of data. So the first thing that I want to do is put in my upper limit, which in this case I'm going to say is 3. And then after that I am going to put in an array of the expected results and hope that it lets me get away with this. So this is upper limit, and this is an int array called expected results. There we go. So upper limit is going to get passed into here, and expected results are going to come down here. So what we're going to do is do a collection assert. Assert collection I forget if this is gonna work the way I expect it to or not. We'll find out, I guess. If 2 arrays are, well, hey, worth a shot, you know? And this is simple enough that I'm not going to really worry too much about it. So I am now going to change from doing my little single check to doing one of these. And you know what? We're doing a full collection comparison as our goal, so I'm going to ignore that for now. We're going to see if it gets me back the right set for that. I expect it to be 2. Cool. Not bad. All right. I'm going to call that a win. So return expected primes given how about for limit? Specified limit? Okay, so our next one, we expected 2 and 3 given a limit of 4, so we can do that same one here. So we're going to give a limit of 4, and we're expecting to get 2 or 3. So let's go ahead and get rid of this test, because we basically just did it again. And to confirm that that really is working the way we expect it to, we're going to add the next one, which we're expecting when we go up to 5 to have the same set of data, because that's an exclusive upper limit, so 5 won't get us all the way to 5, but 6 should get us to 5. So we want to make sure that we can get that without getting the 4, and right now it should break on this for 2 of those. So we'll see what it gives us here. So we got a failure on 2, 3. Okay, so one thing I want to point out here. Notice that as we're digging into this, we say, okay, get primes under should return expected primes for specified limit. And if we look at these, we'll see return expected primes for specified limit, upper limit 3, expected results 2. So it's telling us right here. So we're getting this really, really nice visual of exactly what it's looking at and where it's failing. So I don't even have to click on this to know, okay, so 5, we're getting something wrong when we're passing in 5 and 6. Now, it didn't tell me exactly what this one is, but it still works pretty well. So this first piece here, we got back a 4, and we shouldn't have the 4. So we need to tell this prime list generator to throw that thing out, because we don't want it. So our problem is we're not checking for primes, clearly. So first off, I'm going to change I, and I'm going to call it possible prime, because we're not certain it's a prime anymore. We were a minute ago. That's why we were just including them all. So now I want to write is prime, because I'm a proactive developer, and I am aware that I should just make a method, because why not? So I make a private method is prime. It's going to throw. I'm going to go ahead and just cut this, move it up here, and get rid of my extra paren. And we should now be able to get a throw not implemented exception on all of those, but I don't really want that, so I'm just going to return true. And then this should give us the same result that we had before. It's just now I've buried this inside of a method. And we should include all potential primes, and okay. Same result as before. These two are failing. So now, how do I make these pass? So what I need to do is determine if a number is prime. So there's a quick, easy way to do this. What I want to do is pass in possible prime. I'm going to go ahead and add that as my possible prime. And then the next thing I'm going to do is say... Actually, I can do this the silly way. So I'm going to say if possible prime mod 2 equals 0. So what this means is the modulus operator is basically, it tells it do a division and just return the remainder. So possible %2 means take possible prime, divide by 2, get the result. So say it's 3. So it'd be 3 mod 2 is going to be 1, and say, does 1 equal 0? No, it doesn't, so it's going to return true, it's a prime. So right now, this, if I do a return false here, then this code is now going to claim that all odd numbers are prime and all even numbers are not. So this is going to break something, first off. So this is going to fix 4. It's going to fix everything, but it's going to break this one right now, because we are comparing this against 2. So watch as I run this. And we get back this result, and oh, I broke them all. Hey, go me. Yep, I returned back all empty collections. Because on this one, I returned back true. I knew that was going to break. This one, oh, right, because I'm always excluding 2. Yeah. So 2 has been removed from the set, and we're confirming that 2 is in all of them. So of course it's going to fail them all. Okay. So we want to say possible prime does not equal 2, and possible prime mod 2 equals that. Okay. So now we're expecting it to work. Okay, so everything passes now. And all we had to do was exclude 2. Okay, so when is our next failure? Because I could just keep adding these for a while. So I need a more specific case. So I need something that's not divisible by 2, but is divisible by 3. And the first thing that that's going to run into is going to be 9. So we need to go up to the number 10. And we want to make sure that this does not include 9. So 7, we don't have 8, we don't have 9. Okay, so given the upper limit of 10, we're expecting 2, 3, 5, and 7 to be our results. When we run this, 9 is going to show up in the collection, and our test is going to fail. So our test has failed, and the reason why is that 9 was included in the collection. So the easy way I could do this is I could just say, hey, yeah, let me make another one of these, and just say, hey, you know, if it isn't 3, and, you know, mod 3, return false, and I can run this, and that works fine. But, you know, having written this, let's go ahead and change it to a for loop of some kind, because clearly we know that we're going to have to do this consistently. So the first thing I'm going to do is put in a loop, and I'm going to call this... These are the numbers we're trying to divide into. We're checking to see if these are divisors. So I'm going to call it divisor. I could call it possible divisor or potential divisor, but that seems a bit long since it's really, you know, these are divisors, we're dividing by them, you know, whether it comes out even or not, you know, I'm going to call it that. Okay. Obviously, no divisor could ever be larger than the number itself. So I'm going to go ahead and say possible prime. The next thing is that clearly we don't want to divide by 0. This is divisor, so I should start it at 1. However, every number is also divisible by 1, so I should start it at 2. Also, another thing of note, I did a less than, not a less than or equal. I don't need to check the number itself, because remember, all numbers are divisible by both 1 and themselves, whether they're prime or not. It's just the prime ones have only those 2 as divisors, so we shouldn't check 1 or itself. So we're going to start at 2. And go up to itself. So now what we're going to do is take this same code here, bring it up here. Now, the reason we're writing it this way is the only way to really prove that a number is prime is to make sure that you can't find any of the divisors for it, because really the definition of prime is that it doesn't have any other ones. It's not, there's nothing really special about primes, except that they don't have extra divisors. That makes them useful for some mathematical stuff, but we're not going to get into that. So we're going to go ahead and put in the divisor here and see if this works. So hopefully I didn't break anything, cross your fingers. And we went from that to that. Alright, so let's go ahead and add our next test here. So the next prime is not 9, it's not 10, it is 11. And then it's not 14, it's 13. And it's not 14, it's not 15, it's not 16, it is 17. And 18, 19 is 1. So we're going to go ahead and put in 20. We're going to go up a little ways, so yeah, I know that's a bit of a jump, but I just wanted to get to this. So this gets us a couple of things. So this has gotten past both numbers only divisible by 4, and it, well, no, has it gotten us past any, no, 4 wouldn't be one. We need numbers, so we did numbers divisible by 3, we need numbers divisible by 5. So I just want to make sure I get to a test that really does confirm something for us. It's not 22, 23 is prime, and 4, 5, 6, 19, 23, 25, not 27, 29 a prime? I think 29 is prime. So if it's not, I'm not thinking of its divisor right now. So let's go ahead and run this, see what we get. Okay, so what's nice here is we've gotten past 9, 16, and 25, which are special because those are squares of the numbers 3, 4, and 5 respectively. Also, we're past 4, which, you know, again, but that was an even number, and we know we nuked those right away. So that seems to work pretty well. So our code seems to be doing the trick. So I'm going to go ahead and use it right now. So this is the point where we expect someone to basically be done. This, where is it? This code works. This is the naive approach. It does, the simplest way to get this stuff to work. Technically, someone might have taken this up to 100 and checked a whole bunch of unneeded things where they were trying to divide in numbers larger than the other. It would still work fine, except that they would have divided by themselves. So no, this is going to be about as simple as it gets. So what I'm going to do here is I am going to get my prime list the same way we do here. I'm going to put it in a for each, and I'm going to console write this thing out. So it's not going to be pretty, and it's going to be slow, and it's going to be garbage. But that's fine. So these are primes. We're going to import that library. Our upper limit is going to be 100 for now. And we are going to console write it, and I am not going to currently worry about the trailing comma. However, I would usually tell people to get rid of that eventually. Right now, whoops, primes? No, not primes. Prime. Don't mind me. Oh, right. If I run it out of there, it appears on the other screen. So we're going to run it in here. And hey, there we go. 2, 3, 5, 7, 11, 13, 19, 17, 19, 23, 29, all the way on up to 97. That looks right to me. Okay. So, from here, we can get primes under should make a couple of changes. So the first thing I want to do is add a couple of zeros to this. Whoops. Add a couple of zeros and run it again. And alright, that took a little while to get up to 100,000. Let's add another zero. Try running it again. Whew. Okay, yeah, that's starting to slow down a little bit. Add one more zero. Let's see how fast my computer is. And it's going. Should be 10 times as long as the last one, at least, probably. Probably worse. Yeah, this is going to go a while. Alright. What were we trying to go up to here? We were doing, let's see, 1, 2, 3, 1, 2, 3, 4. Oh, and if you didn't know you could do this, you should check out my What's New in C# course, because numeric literals can now have underscores in them. This has been in here for a little bit, so welcome to modern C#. Isn't that cleaner? So if you ever have to do anything like that, just toss in the underscores. Makes it a little clearer. So what I want to do is make this do a few fewer steps. So we already have these tests that pretty well confirm that this is working right. I don't really want to add more tests because that's just going to be clutter we're going to have to maintain. I guess I could add more test cases, and that's not a huge deal. However, what I want to do is try and reduce the number of operations it's doing. So let's think about a couple of things. So first off, we already have the short circuit here. We're not continuing on the loop past having already found one, so that's good. I don't think we need to go up to this limit when I'm looking at this. So I happen to know that the possible primes here, that we don't need to go up that high. So a couple of things I want to think about. There are divisors of a number. So let's think. If we have the number 100 as a number we want to check to see whether or not it is prime, the first thing that I can do is attempt to divide by 1. And by attempting to divide by 1, I am going to find that I get back 1, and 100 is my result. When I divide by 2, I'm going to get by 50. When I divide by 3, it's not going to work, but when I divide by 4, I'm going to get 25. When I divide by 5, I'm going to get 20. 6, 7, 8, 9, again, not going to work, but when I get to 10, I'm going to get back 10. Then I'm going to keep going up, and I'm eventually going to get to 20, and I'm going to get back 5. And then I'm going to get to 25, and I'm going to get back 4. Then I'm going to get up to 50, and I'm going to get back 2, and then I'm going to get up to 100, and I'm going to get back 1. Now, obviously, since I did the exclusion part, I didn't actually go all the way up to 100. I can remove this one. Since I didn't do the 1, I can remove this one. And then these are the numbers we checked. Now, what's interesting about this is that we checked all, so these are all the ones that would match up for this. These are all the divisors that we could find. Now, because we short circuit and we do this return false, we left right after we found this 2, which is good. It is good. So the reason I bring this up isn't for the case of 100, where we would have exited immediately. I'm more thinking about how we handle the prime, because a prime number, unlike these ones, is going to keep on going because we have to check everything. So we have to go all the way up to the prime. So our highest number was 97, you'll remember. So we take a look at this. If we just went to 100, it was 97. Just trust me on that one. So for 97, we had to check 2 through 96 just to confirm that this was prime. And that seems like a lot of effort just to make sure that that's prime, because I think we could have stopped a little early. So here's the thing that I want you to notice. The numbers that we found divisors for, we divided by the numbers on the left. So that's our divisor, and I forget what it's called. So divide by the number on the left, we get the number on the right. Okay? What you'll notice is that they start repeating. So I start having the results down here. So these numbers, they've all been repeated. Because the 20 was already there, we found it when we got the 5. The 25 was already there, we found it when we divided by 4. 50 again with 2. So I don't need to check these. Now this one is an interesting one, because the 10 is the same on both of them. So the 10 we need to check. So, because clearly we don't, like, once we've divided by the left-hand side, we don't need to divide by the right-hand side, so we can just nuke those. Now this number is special. I think everybody can tell that this is the square root of 100, so 10 squared is 100. So what we end up with here is, we end up with a nice little trick, which is that we only have to go up to the square root. And the reason for that is that whenever you have divisors, they always come in pairs, except for the square root, and the pair always has a lower and a higher. So if we say that the square root is the largest lower one, then what that means is that we never have to go beyond it. Because clearly anything larger than this is going to have a pair that's smaller. This is going to be the largest one. So we're going to go ahead and use the math library and say math.sqrt for square root. Now this is going to get us back a double, because clearly the square root of 97 is not an evenly divisible number, as it's not one of the squares. 100 obviously came out nicely to 10, but an 81 is going to come out to 9, but 97 is going to be this big garbled junk. And so we can still, when we do our comparison with the integer, tell that this divisor is less than the number, and it'll work out just fine. So this is actually not going to work, and you're going to see why in a second. I'm going to go ahead and run the test, though, and we need to make one other adjustment, and that is to handle the squares themselves. And the reason is that we said we did need to check 10. So for the number 4, for example, the square root of 4 is 2. We need to actually check that. And if you look, we set our upper limit to be less than the square root. So we said less than 2. So we now need to add equality. So if you take a look at the results, you'll notice we included 4 in there. And we probably also, yes, we would have included 9 also. That's what the ellipses are there for. They're telling us that there was more in that other than that one. So what I'm going to do is I am going to go ahead and add the equals sign right here. So we're going to say less than or equal to. And we're going to go ahead and run those tests again. Whoops. Let's go ahead and do that. Okay, so now everything works as expected, and we are getting our nice results. In theory, should be a little faster. I think you guys remember how we let this run for a little bit and didn't get back any results. So now that we're only going up to the square root, hey, that is much faster. I mean, it's still taking a while as it prints it out, but that's not the calculation. So that little piece alone meant when we checked 97, for example, all we had to do was go 2, 3, 4, 5, 6, 7, 8, 9, and then we didn't even check 10. So that works out nicely. Okay, so a couple of things still. So I think we can get this a little bit faster still. There's a couple of tricks. Some people like to go this route, which is they'll add in 2, and then they'll make this loop only get the odd numbers, so they'll do a plus equals 2 instead of that, and so they'll only be on the, so they'll start this at 3, and then they'll say like possible prime plus equals 2, and then they'll do something like, if exclusive limit is greater than 2, then prime under, and they'll add 2 or something like that, right? And just hard code in the idea of 2, and then only do those numbers, so they don't even have to bother with doing the method and check of 2, which is an okay trick. So I mean, we can run that as long as I didn't screw up any of the code there. A test should run, and it should be fine. It is. So now we've reduced. So we cut out about half the numbers we even bothered checking. So this should be a little faster. I'm not timing it, but it shouldn't be bad. So there, still pretty quick. So let's see. The next thing. So I mentioned for 97. I like 97. It's a good number. It's going to help us out. So for 97, we check 2, 3, 4, 5, 6, 7, 8, and 9. So 2, 3, I agree. We need to check those. 4? So the interesting thing about 4 is that it is a multiple of 2. So any number that's divisible by 4 is also divisible by 2. So 16, well, it's divisible by 2. 12 is divisible by 2. 20 is divisible by 2. 40 divisible by 2. Any multiple you can come up with of 4 has 2 as a divisor, clearly, because it is a multiple of that. Alright, so what about 6? Any number divisible by 6 is also divisible by 2 and 3. The same is true for 8. 8 is going to be anything divisible by 2, anything divisible by 4, but again, we didn't even need to check 4, so it's going to be all the 2's. Anything divisible by 9 is divisible by 3's. So that actually means one thing. We don't need to check any numbers that have any other factors. So what that means is we only need to try to divide by prime numbers. So for 97, we only need to check 2, 3, 5, and 7. That's pretty nice. Oh, man. It'd be useful. Is if someone, say, wrote a class that, was keeping track of prime numbers or something like that, that would be nice. So I made this thing static. Now, I can keep it static, or I could change it. For now, I think I'm going to keep it static. I have this prime number list that I've been building up from the bottom the whole way. I think that I want to pass this in. Whoops, not there. Don't mind me, right into here. So those are the primes under the possible prime now. That actually, name actually made some sense there. Okay, so I now have this list of primes. So now I can say, I'm going to say primes where prime is less than or equal to the square root of possible prime. So this will get me the primes to check. So I need to check only prime numbers that are less than the square root of the number I'm checking. So now I'm going to say for each prime to check, I'm going to call that a known prime, and then we are going to say if possible prime divided by the known prime equals 0, return false. And I'm going to get rid of this old method because I don't think we need it anymore. So the first time through this, known primes is going to be empty. We're not even going to check it, so we are going to return true. That's going to be for the number 2. That's going to work out great. Actually, we're not even going to check that because we added this. So it's going to have the number. So we're going to come in with the number 3. We're going to be checking 3. We're going to have the number 2. 2's not going to divide in, and so we're going to bail out. Actually, it's not even going to get it because it's less than the square root. So let's go ahead and see what happens when we run our tests. Let's see if I broke anything. Okay, seems like it still works. Now let's see if this code is slow at all. I don't actually know how it's going to be, because that where check might slow it down a little bit. Yeah, see? We're now in memory, so this isn't seeming quick right now. Yeah, that is slow. Alright, so I'm going to do a couple of things. Let's go ahead and get the square root. We're going to get the square root of our possible prime and call this the upper limit. Because we don't want to calculate the square root every time, because that's probably slow. We're going to put it in there, and then we're going to say primes under that, where primes upper limit. So this might speed it up enough. Not 100% on whether it will, but there's another check we can still do. Yep, still taking too long, I think. Okay. So the next thing that I'm going to do is I am going to get rid of this where and just put this on here, and I'm going to say if possible prime is less than or equal to the upper limit and that. Let's make sure I didn't. The tests are here to make sure I don't mess any of this up. Okay, good. So I messed one up. I messed something up. Let's see what it is. So we included 9. So we included that. So at 9, let's see what would happen. So we come in with 9. Possible prime is 9. And then we're saying You know, I'm going to ignore the upper limit for a second because I think that's messing me up. My brain's just not working today. Sorry, guys. I'm a little light on sleep. So I'm going to remove that. Okay, so everything works fine. So clearly, I was getting to a return true because I wasn't checking high enough. So I want to say if my known prime... So I want to get out of here once we're past my number. So if known prime is greater than the upper limit, then I just want to break out of this. I think. Right? And then return true because we got past all the numbers to check. Okay. Yeah. Okay, that should work. Loop through that, break, redo that, and then that should be better. So let's go ahead and take a look at this code again, see if it runs quicker now. Yeah, that wasn't bad. And obviously if we shrink this down a little bit, it should be nice and fast. It's doing a compile first. Now when we run it, it should be a little bit faster, see? So that's not bad. And you'll notice that adding the extra 0 did not actually significantly slow it down. Let me do the build as a separate operation, just so we don't have to wait for that time on the first run. So, see? Even with 1,000,000, still not very slow. You know, not significantly different from the 100,000, I should say. Because we're checking about the same number of items for each of these. So even when we go up to 10 million, yeah, see? It's still not very long that we have to wait for that to happen. So that's not bad at all. Obviously, the printing, this is a console window here. I might just kill this, because that's going to go for a while. Okay. So, not bad. That works out pretty nicely. And all we ended up doing was this code. So, I don't even use link in here anymore. Now, are there more efficient ways to do this? Yes. Could we improve this code? Yes. I think we always can. What's interesting here is that we were able to write this pretty easily, pretty quickly, and I think it turned out well. Now, if memory is not an issue, and depending on the structure and things like that, there are other ways of calculating this where you keep track of numbers the whole time and you adjust down your list as you go. Whatever you want to do, that's up to you. There's other ways of solving this, but again, just an exercise. I think that's about all we're going to do today. I know it's not a very long stream today. I think you'll all forgive me for that. I do have some other things I have to work on. So, it's been fun. I'm probably going to commit this, send this up to the GitHub for dev chatter. My plan is to start having anything we're working on be set up in dev chatter before the stream starts, so we can be committing the whole way through. This was kind of bugging me as we went, that after each green I wasn't committing, but I still think it worked out nicely anyway. Next thing I do want to talk about is the next stream is going to be on Thursday. I'm hoping we don't start too late. I will be a guest on C# Fritz's stream, and so he and I will be working on some testing for his open source projects. So C# Fritz, if you don't know, that is a good stream to check out. It is spelled exactly the way you think it is. So CSHARP and FRITZ, all one word. So twitch.tv/C#Fritz. Right after his stream is actually when mine will be starting on Thursday, so it'll be 12 p.m., so noon, Eastern time. And then, yeah, so we will catch you then. till then, have a great day, happy coding, and yeah, take care.